Good morning, everyone, and thank you for joining us today. We have an exciting episode ahead, packed with valuable insights, so please stay with us until the end as we dive deep into the latest developments in generative AI. Let's get started. In our last deep dive, we really dug into the ghost in the machine, uncovering how AI mastered the art of language. But there's that old saying, a picture is worth 1,000 words. So today, we're making a big shift. We're moving from text to texture, from prose to pixels. We are stepping right into the AI artist studio to figure out how a machine learns to take those 1,000 words and turn them into a single, coherent, and honestly, often breathtakingly beautiful image.
So here's our game plan. We're going to trace the entire evolution of AI art through 5 key sections. We'll kick things off with the early genius of GANs. That's the tech that first really cracked photorealism. Then we'll unpack the diffusion revolution, which is the engine behind all the amazing stuff we see today. After that, we're going under the hood to check out the engine room, the data, and the translators that make it all possible. From there, we'll explore the artist's toolkit. And finally, we'll take a look into the future of AI art and some of the really complex questions it brings up. All right, let's get in.
Okay, so our journey really has to start at the beginning, with the first massive breakthrough in AI image generation. This first section is all about that foundational tech that first let an AI dream up faces and scenes that, well, looked completely real. And just as importantly, we're going to look at why that same technology ultimately hit a dead end.
So, our first question is a big one. What was the architecture that first really pulled off photorealism? Before the current explosion of text-to-image models like Midjourney or DALL-E, the undisputed kings of this domain were something called Generative Adversarial Networks, or GANs for short. This was the technology that proved, for the first time, that machines could not only generate images, but generate images that could completely fool the human eye.
The whole idea behind a GAN is just brilliant. It's basically a two-player game. First, you've got the generator, which you can think of as an AI forger. Its job is to create a fake image from just random noise. Then, on the other side, you have the discriminator, which is like an AI detective. It's been trained on thousands of real images, and its only job is to spot the fakes. The two of them get locked in this relentless adversarial loop. The generator gets better and better at making fakes to try and fool the discriminator, which then forces the discriminator to get better at spotting them. The end result of this high-stakes digital cat-and-mouse game is that the generator becomes an unbelievably skilled artist, or forger.
Now, this whole adversarial process, it really hit its peak with a very specific type of GAN that ended up becoming a viral sensation. And that brings us right to our next question. What was the key innovation that made Style GAN so incredibly powerful?
Right, so the absolute pinnacle of GAN technology was a series of models from NVIDIA, and the most famous was Style GAN. It was trained on these super high-quality portraits, and it could just produce an endless stream of unique, photorealistic, and totally non-existent human faces. The core innovation here was that it separated high-level style attributes, so things like a person's pose or their identity, from all the random low-level details like freckles or skin texture. This separation gave people incredible control over the output, and it led directly to that famous website, This Person Does Not Exist, which showed you a brand new, perfectly fake human face every single time you hit refresh.
But for all their power in a very specific area like creating faces, GANs had some pretty fundamental limits. And this leads to a really crucial question that explains why we're not all using GANs today. Why did they struggle so much to become the engine for the text-to-image revolution? Well, it turns out GANs had 3 fatal flaws. First, training instability. That two-player game is a super delicate balancing act that can just completely fall apart. Second was something called mode collapse. Basically, the generator would find one little trick to fool the discriminator and then just repeat it over and over. It gets stuck in a creative rut, like an artist who can only paint golden retrievers. But the real deal breaker, the thing that really held it back, was the control problem. There was this fundamental mismatch between the model's goal, which was to fool the detective, and a user's goal, which was to create a specific image. You couldn't just commission an astronaut riding a horse, because the GAN just wasn't built to listen to your instructions. And this limitation, it left the door wide open for a completely new approach.
So the limitations of GANs really paved the way for a whole new way of thinking. And that brings us to the technology that solved that control problem and really unlocked the current era of AI art, diffusion models. This is the elegant and incredibly powerful process that's behind all of today's state-of-the-art generators.
So how exactly does this new approach work? Well, it's a completely different philosophy. Instead of that competitive, adversarial game that a GAN plays, a diffusion model works much more like a sculptor. It starts with this formless block of marble, or in this case, a canvas of pure digital static, and it meticulously chips away, step by step, until a coherent image finally emerges.
The magic here is really a two-part process. First, during training, you have what's called the forward process. The model takes a real image and systematically adds a tiny bit of noise. Think of it like old-school television static, over hundreds and hundreds of steps until the original image is just completely gone. The key is that the AI learns to predict the exact noise that was added at every single step. Then comes the reverse process, the creative part. It starts with a fresh canvas of pure static and uses a neural network to predict and then remove a tiny bit of that noise over and over again. And with each step, that static slowly forms edges, then it forms shapes, then textures, until a completely new image is revealed. It's pretty incredible.
Now, that process on its own would just create a random but probably high-quality image. So how do we get it to create the specific image that we actually want? Well, this brings us to the final critical piece of the puzzle that turns a diffusion model into a text-to-image generator. It's called text conditioning.
Think of text conditioning as the steering wheel that gives the artist control. Your text prompt, let's go back to an astronaut riding a horse, gets converted into a really rich numerical representation. It's called an embedding that captures its meaning. Then, at every single one of those reverse denoising steps, this text embedding is fed into the network. It acts like a constant guide, telling the network, hey, don't just remove any noise, remove noise in a way that makes the final image look more and more like an astronaut riding a horse. It's that constant guidance that allows the model to sculpt your vision out of random stat.
And for those who really want to get into the technical weeds, to achieve even greater precision, researchers have developed advanced techniques like inner control. Instead of just checking the final image at the end to see if it's accurate, inner control enforces consistency during the entire diffusion process. It trains these little lightweight probes to check the work in progress against the control signal, like a depth map or a human pose, at every single step, and it does this deep inside the U-net, which is the core neural network doing all the heavy lifting. By constantly correcting the course like this, the model drastically reduces errors and creates a final image that is so much more faithful to what the user actually wanted.
So we have the process, but what's the fuel? What powers it? Well, that brings us to the engine room. A generative model is only as smart as the data it was trained on. So to generate an image of literally anything you can imagine, it first has to be shown a picture of, well, almost everything. So let's look at the data and the translation tech that makes this whole thing possible.
So, to teach an AI about our visual world, you need a library of that world. So what is the library that these models are reading from? Well, that would be massive data sets, the most famous of which is probably Lion 5B.
Let's just pause for a second and appreciate the scale here. LAN5B is an open-source dataset that contains over 5.85 billion image-text pairs that were scraped from the public internet. This is the massive visual dictionary that gives these models their incredible range of knowledge. It has everything, from famous landmarks to anime fan art to scientific diagrams. But because it's an unfiltered reflection of the internet, it's also the source of many of the model's biggest problems. Because it contains all of our societal biases, copyrighted material, and harmful content that the labs are constantly trying to filter out.
Okay, so having billions of image-text pairs is one thing, but how does the AI learn the actual connection between a pattern of pixels and the word dog? This is where a really crucial piece of technology comes into play, one that acts like a universal translator.
The big breakthrough here was a model from OpenAI called Clip, and you could absolutely think of it as a Rosetta Stone for AI. It was trained on hundreds of millions of image-text pairs by playing a simple but absolutely massive matching game. The model gets shown a whole batch of images and captions, and it has to figure out which caption goes with which image. By doing this millions and millions of times, Clip learns to create this shared embedding space where the numerical representation for a photo of a dog is really close to the representation for the text, a photo of a dog. It's this Clip model that translates your prompt into that meaningful guide that steers the whole diffusion process.
All right, now that we get the core tech, let's look at how people actually use it. Because the AI isn't just a vending machine you put a prompt into. It's a full-featured artist studio. This section covers the tools and the philosophies that really define the user experience today.
The main way we interact with these tools is the prompt. And the art of crafting a good one, prompt engineering, has really become a new kind of creative skill. The difference a well-crafted prompt makes is just dramatic. A simple prompt like, a castle, will give you a pretty generic image.
but an engineered prompt that specifies the style, the composition, the lighting, the mood. That produces a vastly more specific and often much better result. This is also where users can start to mimic the style of famous artists, which is one of the most powerful and, frankly, most controversial features of this technology, raising all sorts of complex questions about artistic ownership and emulation.
Now, as these tools started to come out, two very different philosophies emerged. On one hand, you have Midjourney. It's a closed commercial platform, and it's famous for its highly stylized, often very painterly images. The company has essentially curated its model to have a very distinctive, opinionated look. And then on the other hand, you have Stable Diffusion. Its release back in 2022 was a huge moment because the model was made open source. Anyone could download it, run it, and modify it, and that sparked a Cambrian explosion of innovation, creating this decentralized global community that's now building thousands of new tools and custom models on top of it.
So, we've journeyed through the architecture, the data that fuels it, and the tools that we use to control it. So where does that leave us? Let's take a moment to summarize what we've learned and then look at some of the profound and still unresolved questions that lie ahead for AI-generated art.
So what's the big takeaway from all of this? I think it's this. By learning the incredibly intricate relationship between words and pixels from billions of examples, diffusion models can now create these stunningly original and photorealistic images. These tools are way more than just image generators. They really represent a whole new medium, and they place a tool of immense creative power into the hands of anyone with an imagination. But of course, this incredible power also raises some profound legal and ethical questions. And this brings us to the great unresolved debate. Who owns this stuff? The global legal landscape is a complete patchwork right now. It's evolving, and there's no real international agreement. In the US, the Copyright Office has been pretty firm. A work generated entirely by AI is not eligible for copyright without significant human input. The UK, on the other hand, actually has a provision for computer-generated works. Meanwhile, the EU, much like the US, doesn't currently grant copyright to fully AI-generated works. This really messy legal framework just highlights the fundamental challenge these technologies pose to our existing ideas about intellectual property. So we've explored how AI learned to understand our language and how it learned to see our world. But what about its sense of hearing? In our next deep dive, we're going to explore the unheard note and investigate how AI is being trained to compose music and generate sound. You know, as these machines get better and better at showing us exactly what we ask for, the real question becomes, what should we be asking them to create? Thank you so much for watching. If you enjoyed this, please subscribe, like, and share, and don't forget to hit the bell for more from Tech AI and beyond.